Okay, this is AP Stats. We're going to do section, actually, we're not going to do all the section, but we're in chapter 7.3, which is sample means. And before I actually start this thing, please make sure that you actually go and read section 7.3 so that this will make much more sense to you instead of just listening to me do a bunch of problems, because, well, that might get a little boring if you don't know what you're doing. Okay, so for starters, we're going to start with slide number 5 from the PowerPoints, and this is example number 8 in the book. Sulfur compounds such as dimethyl sulfide or DMS are sometimes present in wine. They cause off orders. Extensive studies have found that DMS orders of adults follow distribution with a mean of 25 micrograms per milliliter and a standard deviation of 7 micrograms per liter. That's the other bit that we need. Suppose we take a simple random sample of 10 adults and determine the mean order threshold X for the individuals in the sample. So that means our N is going to be equal to 10. Okay. Now, this comes from sorry. So what is the mean of the sampling distribution of X bar? And then explain how we got that. And then what's the standard deviation of the sampling distribution of X bar? And then check that the 10% condition is met. So the first one, part A, if you'd read, then it should be pretty obvious since X bar is unbiased. Okay, then we can say that the mean of X bar, right, of the sampling distribution of X bar is going to be equal to the mean of whatever sample distribution we have in the first place. So that's just going to be 25 is it micrograms? Micrograms. Okay, per liter. All right, and then part B for this one, what's the standard deviation? So if you'd read, then the formula that goes with this, the standard deviation of X bar is equal to the standard deviation of your sample proportion. Sample, whatever you have in this case. What do we have? 7, okay, over the square root of your number of samples, or the number of your N. I'm too tired right now to figure this out. So 7 over the square root of 10 in this case. So we have standard deviation of X bar is going to equal to something around 2.214. All right, and then to check our 10% condition, the question basically is 10, which is what we got for the number of adults in each sample, is that going to be less than or equal to 1/10 of our entire population? And so, yeah, that pretty much works. We need at least 100 in here. I'm sorry. Because 100 is going to, 1/10 of 100 is going to give us 10. So do we have at least 100 people in our population? Yes, we do. So we're good to go. We have at least 100 people in our population. So 10% condition has been met. All right, that was slide number 5. Okay, more importantly is the two formulas that I used. So we have the standard deviation. X bar is the standard deviation of your sample divided by the square root of, well, in this case, the number of adults. And then this one works out too, since X is unbiased. And we checked our 10% condition, so we're good to go. Okay, slide number 7 is the next one. And this requires just a little bit more work, but it's not too crazy. Okay. We're going to pretty much do the same thing that we did for the previous one, except take it to one more step in finding the actual probabilities. Basically, our normal. So the height of a young woman follows a normal distribution, which is good to know. Okay, with a mean of 64.5 inches and a standard deviation of 2.5 inches. So find the probability that a randomly selected woman is taller than 66.5 inches. Shorter work. So this is part A is literally chapter 2, chapter 5. You know, everything pretty much chapter 2 almost what we've done before. So there's your normal distribution. We've got a mean of 64.5. We want to know what's the probability that she's taller than 66.5 inches. So this is 66.5 inches. We want that probability. Okay. I'm not gonna bore you with this. You should be able to figure out by now how to figure that out. You should get, if you're doing this correctly, if you're doing it on your own and you're doing it correctly with your z-table, you should get a probability over here of 0.2119. So about 21.2% chance that a randomly selected woman is taller than 66.5 inches. Okay. Alright, that was part A. Part B is where the new stuff comes in. So find the probability that the mean height of a simple random sample of 10 young women exceeds 66.5. Okay, so you're not going to do the same thing, obviously, because that would defeat the whole purpose of part B. But you will take pieces of what you did in part B and use it. So, we want to still know, right? Here's our distribution. Here's 0.5. We want to know still 66.5 inches, but this is not just for one person. This is for a simple random sample of 10 young women, right? So we picked 10 of them, right? We reached into the, like we did with the activity, reached into the bag and pulled out a certain, in this case, we pulled out 10, and we want to know what's the probability that mean is going to exceed 66.5 inches. All right. So, we know X is unbiased, hopefully. And so in this case, the mean of X bar, right, the mean of our sample being 10 young women, is going to equal the same thing as the mean of our actual distribution. In this case, it's going to still equal 64.5. All right. But the standard deviation follows the standard deviation of your distribution divided by what your sample size was. In this case, it was 10. So we have 2.5 divided by the square root of 10. So our standard deviation here is going to equal 0.79. All right, so these two, okay, I'm going to use these two, right, and use it in terms of my curve now. So instead of using, what are we using the other one? Instead of using 2.5 like you should have in part A, then I'm going to use 0.79 instead. So I need a z-score of, let's see, I want my observation subtracted by my 64.5 divided by my new standard deviation, 0.79. I should get a z-score of 2.53. Okay? So now the question is, on the z-table, the probability of getting a z-score that's more than 2.53 should be equal to something around, if you're doing it correctly, you should get a probability of, what is it, 0.006, somewhere around there. Or, sorry, 0.0057. Sorry, that was wrong. All right, so somewhere around 6%, or less than 6%. Sorry, 0.6%. So approximately, so the area under here should be, so your z-score is 2.53. You take away from 1 whatever you find at 2.53, and you should get 0.0057 over there. So approximately 0.6%, right? So less than a 1% chance that in a simple random sample of 10 women, the average height is going to exceed 66.5 inches, which is probably not very likely. Okay, so less than a 1% chance. So it's probably unlikely that you're gonna have that actually happen. It's less than 1%. All right, that was example number 9. Slide number 7. All right, next one. Slide number 8 is the next one. So sampling from a normal population, the length of the human pregnancies from conception to birth varies according to a distribution that is approximately normal, with a mean of 266 days, standard deviation of 16 days. Find the probability that randomly chosen pregnant woman, so singular, right, has a pregnancy that lasts more than 270 days. Show your work. So this is going back to, what do I want to write over here? Okay, you can do this on your own. It's not that big of a deal. So there's your distribution. You have 266 days. Standard deviation is 16 days. You want to find out that the pregnancy lasts more than 270 days. You can do this on your own. You should be able to handle doing this on your own by now. And you should get an answer of, where's my slide number 8? You should get an answer of an area under here, or proportion of 0.4013, so somewhere around 40%. Okay? Alright, so there's about a 40% chance that a pregnant woman has a pregnancy that lasts for more than 270 days. Okay. That's like review from chapter 2. Alright, number 2, suppose we choose a simple random sample of 10 or 6 pregnant women. Okay, so we know our n is going to be equal to 6. Let x bar be the mean pregnancy length for the sample. So that means, what do we want to do? The mean, what's the mean of the sampling distribution of x bar? So since, hopefully, we're assuming, it doesn't say, but we're going to assume that x bar is unbiased at the moment. So that means our mean of x bar is going to still equal the mean of our sample distribution, which in this case is still 266 days. Okay, presuming that x bar is unbiased. Estimator of x. Sorry, of mu. Not x. Okay. Alright, compute is it x or mu? No, I can't remember. Okay, never mind. I can't remember what is x bar or mu. Next one, compute the standard deviation of sampling distribution. Check that 10% condition is met. Your standard deviation of x bar is going to be standard deviation of your sample divided by, or is not your sample, population, and then divided by square root of n. So what is this? A 16 divided by the square root of 6. So we get 6.532 days. Our 10% condition, yeah, pretty sure, because we need at least, is 6 less than or equal to 1/10 of our population. So I'm pretty sure our population is going to be more than 60. Because 6 less than or equal to 1/10 of 60 is going to be 6 less than or equal to 6. So our population is more than 60 pregnant women. Sorry, there you go. So we have at least 60 in our population, so we're good to go. Okay, and then number 4, find the probability that the mean pregnancy length for the women in the sample exceeds 270 days. Show your work. Okay, so we want, let's see, 266 is the mean over 270. Our mean of X was still equal to 266 days. We found out our standard deviation of X bar is now 6.532 days. So we want to find basically the probability that it exceeds 270. So 270 minus 266 divided by 6.532 gives us a z-score of, what, 0.61. Okay. And if you look at the z-scores, you want the probability that our... Did I do z on this one? Hold on a second. What did I do? Oh, my bad. On this thing, I should have done x bar. I'm too tired right now. Okay. Our x bar is over 2 point. Right? Yeah. No. I did it correctly. This was Z. Yeah. No. This was Z. Okay. Probably a z-score greater than 0.61 is going to equal to something around, you should get 0.27. So there's a 27% chance of getting a sample of 6 women whose average length of pregnancy is going to be over 270 days. So that's probably very likely. 27% is pretty good. Okay, moving on. Slide number 12. Okay, it's kind of a... Okay, we'll see. Slide number 12, which is actually example number 11. And I'm trying to figure out... This is pretty... Okay, let's see what we're going to do with this one. Okay, your company has a contract to perform preventive maintenance on thousands of air conditioning units in a large city. Based on service records, the time and hours that a technician requires to complete the work follows a strongly right skew distribution with a mean of 1 hour. A standard deviation. In the coming week, your company will service an SRS of 70 air conditioning units in the city. That's important to know. You plan to budget an average of 1.1 hours per technician to complete the work. Will this be enough time? Okay, so what's the probability that average maintenance time for 70 units is going to exceed 1.1 hours? Alright, so this is pretty much the same thing that we just did in the previous one. So, even if strongly right skewed, the central limit theorem states that eventually it will become normal. Okay, so our mu of x bar is still going to be the same as our mean of problem. In this case, is still going to be 1 hour. So 1 hour. And then our standard deviation of x bar is going to be, standard deviation divided by square root of n. So we have 1 hour over the square root of 70. What in the world is 1 over the square root of 70? Actually, I have to work this out. 1 divided by the square root of 70 is 0.1195. So I'm probably going to round this up to 0.12. Alright. So, we want to know that it exceeds 1.1 hours. So, our z-score is going to be 1.1 minus 1 divided by 0.12. 1 minus 1, 1. divided by 0.12. I'm going to get 0.833 and then repeating basically. So the probability should be, okay, so it's going to exceed 1.11. So what's the probability of the z-score being greater than 0.833? And I don't have my z-table with me. Sorry, you can't see that. I don't have my z-table with me right now, so you're just going to have to finish this one on your own. Okay. What is that probability? Or what's that shaded area under there? Okay, number 14 is a slide number 14 through 17 or 18, I can't remember. Slide numbers 14 through 18 is a little bit of an involved problem. So what I'm going to do is stop the video now and then pick it up in the next set. So if you need to do something, go do it now and then pick up on slide number 14 to slide number 18 because it's not super involved, but it'll probably take, well, maybe it'll take another 5 minutes. I think I'll just do it. I'll breeze through it. What time are we at? Yeah, I think I'll stop and then I'll do it in the next one.